Hey, John here. Let's have a look-see at what's in this directory down here, vdp99, which is where our video display processor code is going to go for our Project Nouveau. Last time I talked about this module here, which is a wrapper around the vdp99 module we're going to look at today. The purpose of the wrapper we talked about last time is to deal with all the clock domain crossing stuff so that inside here we don't have to worry about it. Okay? So as you'll see, we'll look through this thing today. This has one single clock that comes in, which is the pixel clock. This whole thing from here down in the project design runs only in the pixel clock domain, not the CPU's phi clock domain. Big thanks to everybody supporting the channel. Please like, subscribe, or join on Patreon. The VIPs listed here deserve a great thanks. Thank you very much for supporting my channel. Okay, so what we're going to do here is we're going to bring in surprisingly few things. This is the entire interface of the VDP, right? Well, I mean, if you think about it, if you actually look at the real chip, it's got 40 pins. It's got the data bus. It's got the 1 bit of address, which is called the mode, which is the least significant address bit. And we got reading and writing controls. It's got an interrupt request output. And it outputs a color. And because we're dealing with VGA instead of, NTSC. NTSC is a single analog data output line, right? So what we're going to have is a 4-bit color. We're going to have a horizontal and vertical sync bit as well to run the VGA, and I talked about VGA before. So if you need help on that, look at the playlist that this is in and scroll back a bit. You can see all kinds of stuff about VGA and its timing and all that fun stuff, okay? Now, when it's instantiated, we're given a parameter for the VRAM size. By default, it's 8K. I got some comments over here because I was playing around with some different sizes. For Project Nouveau, at the moment, I'm running it at 12K. We'll talk more about this maybe some other time. The short of it is that we're trying to make use of all the BRAMs. Fine, I'll talk about it now. Trying to use all the BRAMs that are inside the FPGA. And depending on the number you use, the Yosis compiler may try to optimize the circuitry in ways that you might not think it's going to do. One of which is if you choose an odd number of BRAMs. Remember, the BRAMs on the ICE40 are 512 bytes. So if this is in kilos, it'll always be even. But if this is going to be like 12.5K instead of 12K, what happens is go ahead and set it up and build one like that and see what happens. What Yosis wants to do, at least by default, is use one of the BRAMs as part of the decoding logic to gang all those BRAMs together. Because realize, you think about this, 12K of video RAM that's going to be provided in half K BRAMs, that's 24 total BRAMs. So somebody somewhere has to create a giant mux to take those 24 BRAMs and make it look like one single RAM. There has to be some decoding to choose which BRAM I'm choosing at a time, to enable which one, and then you got to take all the outputs and mux them all back together again, and that's a lot of LUTs. So part of the decoding logic, I think, that's in the circuitry that Yosis is trying to optimize for you, consumes a BRAM of its own. I mean, a BRAM is just a bigger lookup table. In the FPGA, normally there's a whole bunch of these 4 in lookup tables with 1 output bit, 4 bits in, 1 bit out. But a BRAM, if you think about it, is what? If you configure it for, say, 8 bits of output, you've got 9 bits in and 8 bits out. So you can use that as a giant LUT and part of a decoder and choose, which BRAMs are going to get enabled and all this other fun stuff. Anyway, I don't know the specific algorithm it uses, but it's very obvious that that's what it's doing. I even sent a note back to the Yosis team and asked, why is it doing this? Because if I want to use all the BRAMs and I want to divide it up into 12.5K and then another 3.5K or whatever that comes out to, 12.5 and 2.5. And it wants to use one of the BRAMs for its decoder. Now I'm out of BRAMs. The thing won't compile, right? So they responded with, well, this is a feature for reasons along the lines that I just explained. And if you want to tell it not to do that, you can prioritize the use of LUTs rather than the BRAMs for this logic that it's going to generate. And they tell me how to do it. It's a little complicated. And they also included a note that says, yeah, this is not really convenient. Maybe there should be an easier way to do this. But here's how you do it if you really want to. And I don't really want to. I don't want to do it that bad, is what I'm saying. So if you're going to play around with this, be careful. When this number is relatively speaking large, I mean, there's only 16K in the whole thing. If you get cute and start doing 12.5K, which is where I was, it'll surprise you, as they might say. So just be aware of that, okay? The reason this is the way it is anyway, as you might recall, if you rewind a minute, we're using some of the BRAMs as ROMs, so we can boot up the CPU. And, I'm now contemplating what would happen if we don't do that, so we can use all 16K for the VDP, because this is a weird VDP configuration as it is. I only got 12K. It should have 16K, if you really want to be compatible. So down the road, I'll probably figure out some way to dual purpose the memory that I'm using as a boot ROM, because that thing is only used temporarily and then never again after it's done booting. Well, during the booting, it doesn't need the VDP at all. And after it's done booting, it never needs the ROM. So I can dual purpose that memory. And basically, if you think about it, store the boot ROM image in the VDP RAM and let the CPU boot out of the VDP RAM. But I'm going to have to hack this file and be very careful about how I do that. Okay? So I'm not going to confuse matters now. Just understand that this is a weird size. And it would be nice to have all 16K for VDP RAM. But for now, I'm going to run it with 12K for various reasons. Okay? PixClock is the clock domain that this entire thing is going to run in. I mentioned before, reset is going to reset this whole thing if necessary. Down here are these, the input and output signals. Read tick and write tick. We saw that last time. We were talking about the wrapper of this thing and how that works. It's a single tick wide signal in the local clock domain for each one of those two. This is going to be the address mode bit. We have separate data buses for input data and output data because we don't use bidirectional data buses inside the FPGA. It's more convenient to just use two separate ones. And even operating in full duplex if you want to, although it doesn't get used that way. It could be. There's the interrupt request output that we'll see comes out of a special module that I wrote with specifically the VDP from Texas Instruments, the vdp99, the TI-99 VDP. And I did a whole video on why their interrupt output doesn't work correctly. And, yes, we can argue all we want about, well, it was never intended to be used this way. I don't care. If I want to poll a status register, I should be able to poll a status register without having the whole house of cards come down. So we'll have a look-see at that and see how to do it right so that it will tell you the truth and not end up with these race conditions that cause you to miss or duplicate interrupt request status events while polling if you decide to poll the VDP. I'll also add at some point down the road, I have a note. We did a workaround on the Z80 Retro as well, as you might recall, that allows us to see the interrupt request bit from the TI VDP by reading it out of a different register. so that we can still do software polling if we want to. And it should be easy enough to do that in this case. I just have to make it available in addition to the normal place in the status register that we'll see in here. I'll also make it in the wrapper that we looked at last time. I'll add this to some other, status input register that we can read from the CPU and be code compatible, is my point, with the Z80 Retro. And that would be, as you recall, is one of the unused bits in one of the joystick inputs. I already talked about this stuff here, okay? So this is the output of the VDP module. So what then is going on? As we will see in this interface block here, this thing has got, if we scroll down, it make more sense. So we got remember, you got 8 registers as defined in the TI-99 VDP. Here's the manual in here, and you go down here just to remember. They're defined, in fact, they're right here. Here's register 0, has these bits, and so on. And these are write-only registers from the TI VDP. And at the very bottom of this list, register 7, you can write in here. You get 2 colors, the foreground and background color for text mode. And the background color in here is also used for the border, which they call the backdrop. Actually, backdrop is different than the border, I must say. They mean any transparent pixel in the whole screen, as well as the border, when they say this right here. Well, that'll be more subtle. We'll talk about that later. But yes, I don't want to say this wrong, because this will come back to haunt us. So I think of it as the border color, as well as the background and text mode. But it's also, like I said, the color of any pixel that's transparent on the screen. Then you have this status register. So if you read from the VDP, you get to see this thing, which includes this frame flag here, which is the thing about the interrupt request bit that drove me nuts in that other video. This is the place where you can look at and see the interrupt request status bit if you want, okay? What else we got? A collision and a flag and some other stuff related to sprites. I haven't implemented all the sprite stuff yet. I've got a stub in there that does the sprites. If you look at the code right now, as I record this, hopefully in a few weeks it'll all be done and tested, and we'll be done with the VDP. But for now, that's what's going on there. So anyway, that's what's going on. That's why we have these 8 registers here. These are write-only registers, and in this module, when you have the write tick on and you're in the right mode, and there's this little song and dance you have to do to get it in the right state, you then can write into these 8 registers. And this will output these register values. If you look at the module, these are actually outputs. And what I'm going to do down here is, you see the output goes into regs 0, regs 1, regs 2, and so on like that. I have this array of bit vectors here, 8 registers of 8 bits, and then I extract them into these wire names. All right, I could have done this in a different way. I mean, a million ways to do this, I'm sure. This is how I did it. The short of it is, these wires here, some of them are single bits, other ones are vectors, are assigned the values of their respective bits from the various registers. So if you look at register 2, the bottom 4 bits represents the VDP name base, and this thing is going to become an address. It's 14 bits long ultimately, but I'm going to store it in its natural size. Okay, so let's take a look at this. Right, that's register number 2. So we all have our bearings here. 4, 3, 2. You can see 1, 2, 3, 4 of the least significant bits of register 2 are the bits that represent this name table base address. Okay, now in register 2, it's just the 4 least significant bits. In the VDP address space, it represents the 4 most significant bits of where that table starts in the VDP RAM. So what I wanted to do is I took the value out of register 2 and the 4-bit value and signed it to this guy here, name base, and it's only 4 bits long. And later on, when we use it, what'll happen is I'm going to use the bit concatenation, right? So it'll be like an open curly, and then it'll say VDP name base for these bits here, and then it'll be comma, and then there'll be other, variables in here, wires or registers or whatever it is, to concatenate all the bits together to construct this address, all right? So I found that to be desirable. I think that might be a fast way to do it. You don't want to burn up a bunch of LUTs. The naive way to do it would be to store this in a 14-bit value, okay? And then add some value here where these are all going to be zeros. Now, if you did that and your Verilog compilation decides to actually do it with an adder, you're going to burn up tons of LUTs doing all that. This is why I did it the way I did it. It won't do it. It can't do it that way. If you just simply say, take these bits, followed by these bits, followed by these bits, it'll do that. And it's free. You're just moving wires around, which costs you nothing. All right? So that's why all these have weird sizes. These are their natural sizes. When they get used in the places they get used, mostly in the finite state machine, they'll be just bunched together like this, for example. This one is not it using, I'm just creating it. The VDP mode is like really weird. It comes from bits in different registers in weird orders. And this is the bit concatenation I was talking about, right? So I'm going to concatenate the bits just to create a mode, but then I might use the mode in another concatenation, all right? All right, so that's what this is going to do. This includes a finite state machine in its own right, because if we look at the way you write into these registers, you don't just say, here is register 5, store it in there, and you give it an address like you normally would, to a memory byte. No, that's not how it works. If you want to do it here, what you need to do is you store the data byte you want to store in a VDP register into a temporary spot inside the VDP. And then the next time you do a write into the VDP, when you're in mode 1, okay, you give it the number of the register you want to store the previous data into. And these bits up here have to be a 1 and a 0 like this. All right? So this requires a state machine. It has 2 states. You're either, waiting to collect the data byte, or you're waiting to collect the register address, right, that you're going to store that byte into. So if you look at this module, you'll see a little state machine in there. And this takes a write and a read tick as its inputs, and it's only going to generate the write tick if, and as we saw, the write tick that comes into this module, that's this one up here, is already been decoded and everything else. So this is a 1 tick. It's been synchronized, and it only goes true if the CPU wants to write to the address that is the output port for the vdp99, and likewise for reading the input. All right, so what is this thing down here going to do? Well, it takes it one step further. This is going to be a write tick if and only if during mode 1 will that be true, and so on down here. So when we look at this module in here, it'll simply say, I want a read tick, I want a write tick, and it'll only go true if it is true in a meaningful way to the register interface, which is the mode 1 read and write operation, okay? And what else do we got? Here's the data in that is sent in there. This is the data bus from the CPU that is synchronized and latched, we saw last time, and delivered in here, okay? So this is where the state machine will get its data when it's needed. When it is written, the register number is stored in there in that second operation, okay? And then it feeds back to here, like I saw back into these variables up here, through here like that, okay? Here's the RQ generator. This is a pretty straightforward thing. I honestly don't understand why TI decided not to do this for their own, but whatever. It is what it is. It gets the local clock domain, it can be reset, and so on. Just like all these modules, they're always going to get a reset in the pixel clock domain. Then what happens is there's a single tick signal. Remember, a tick signal to me is a signal that goes through with, as a result of a pix clock rising edge, stays true until after the next rising edge, and then it goes false. It's a 1 period long signal. It's very common in synchronous circuit designs to let this know that an interrupt needs to be emitted from the VDP. We'll see this is very simple. This is just the only way we generate interrupts from our VDP is when we finish a video frame so that we can let the CPU know that that would be an optimal time to download a bunch of data for the next video frame. So if it wants to animate something or just scroll text, it would be nice to do it when we're not busy drawing on the video monitor, because you can see the tearing on the screen otherwise. That's the whole point of this thing here, right? So we'll see that that comes from the VGA sync generator at a point in time after the last pixel is drawn on the screen. That is part of what I call the active display region, which are the characters, from the patterns and stuff like that. It's basically going to be the pixel, the first border pixel on the right side, the last line of the screen. Because at that point, no pun intended, that pixel point in time, the VDP will not use any more of the data that's in the VRAM for the current video frame. And you have that'll be the most amount of time you can have before it starts drawing the following frame. So I wanted to do it as early as possible. We'll see that that's the case, and that's what tells this IRQ guy that this is when I want to start outputting the interrupt request to the CPU. The reason there's a read thingy in here, and it's a read tick with mode 1, a mode 1 read is what happens. We were just looking at it. That's what you do to read this status register right here. VDB does this, blah, 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 blah. So why doesn't it say mode 1 right here? I don't know. VDB contains this, that, and the other thing. I don't know. Read around in here. It's probably in here somewhere where it talks about the status register. Actually, I think it is. It's up here. When it talks right into the thing, yada, yada, yada. Reading the status register, you simply do a mode 1 read. There you go. And you'll see this thing. All right? So that's why we have the read signal down there. And this is not that complicated, but it's not trivial either, because you need to make sure that if you're reading and you're generating an interrupt at the same time, that it does the right thing, right? You don't say, here, in the middle of reading, you have an interrupt and then change your mind halfway through because it's generating one and being read at the same time, because the act of reading it will reset your interrupt request status output, right? So they did not do that correctly in the vdp99, shall I say the TI99, but this will do it correctly for us, so you can use it that way if you want. And I would argue it's also fully backward compatible, because if you can't pull the real one without screwing it up, and you can pull mine without screwing it up, it's a subset of the real one anyway, so we're fine with that. Now, the idea of this DMA read tick, as you can see right there, in addition to the regular old read tick and a write tick, so we have two different ways of reading the VRAM, is my point. That's where I'm going with this. And it turns out I found this to be more convenient to just have two different ways to read the VRAM from the finite state machine than to do this any other way. The VRAM is somewhat complicated by the fact that inside here is where I put the logic that automatically advances the addresses when we are using the, oops, I'm going the wrong way here, when we are going to do this. Right? So when you're writing or reading from the VRAM, you might recall that what you do is you send these 2 bytes down here, and then you get to the 3rd byte for the actual data transfer, which is kind of the opposite of what you do when you're transferring to registers. You do the data first, then the address. Now, this one, you do the address first, because what you're going to do is establish the first address. As you can see, the lower 8, the upper 8, and so on. And then you're going to say, read a byte with your mode 0, okay? Mode 1 is you're setting up the addresses for the future data transfer when you're dealing with the VRAM data. And again, these magical 2 bits over here tell the VDP that we're dealing with the VRAM versus a regular register when we're in mode 1. Then you do a mode 0 data transfer. At this point in time, this data here will be stored in the VRAM at the address that you earlier set up in here. It'll automatically increment the address so that if you write another byte in mode 0 after that, it'll go into the next address and so on. And the same thing happens with reading. If you repeatedly read, you get the next byte, next byte, next byte. Okay? And we'll look more closely at that some other time as well. But in short of it, that's what's going on here. Now, the DMA read tick versus this read tick, all this is going on at the same time in here. What this is used for is that the CPU wants to do a read tick, and this is getting stale. I should probably get rid of this comment or change it. I'll do that when we do the video on the VRAM. But what happens is if the CPU wants to read from the VRAM, this would go true for a tick. Okay? If the finite state machine wants to read from the VRAM, which it does constantly, right? It's reading all the pattern tables, name table, all the tables and stuff, and the sprites and everything else to draw on the screen. What it'll do is it will assert a DMA operation, and I probably could have named this something better than DMA because that has other meanings. This is really a priority read from the state machine. It says, I need this, I need it now, I don't care what anyone else is doing, tell them to all blow off, okay? When this is true, that will take place. It'll read from the DMA address, period, and the data will come out in the next cycle. If you're going to use the read and the write tick, what will happen is the data will come out in the next cycle down here, and it'll do it based on the state machine for the register I/O stuff. Okay, so this thing here says here's a full address, the 14-bit address, and I need it now. Down here we'll see the CPU interacting with the registers and playing all the games of the state machine to do this sort of thing. It'll be writing, and then it'll be accessing in this case it's for reading, or it'll do a write and another write down here to write data from the CPU. That'll be these guys down here. So there's 2 different interfaces to this is my point, and they both work differently. This is here and now, as we will see, and these will get deferred because if you think about it, when the CPU wants to write data into the VRAM, it doesn't really need to go right now. It needs to go before, a couple of clock ticks go by, before it ends up needing to use it, which is probably in the next frame that'll be rendered, which is actually usually many, many clock ticks away. Okay? So what you'll see in here is it'll buffer up. If the CPU writes into the VRAM, it'll buffer it up and hold it for a while until it can, in case the main finite state machine for the whole video pipeline is in use right now. When this thing idles out and they're not in this DMA read tick mode, you'll see then it can take care of this stuff. All right, then it would store into the memory's dual ported. So what am I saying? It'll only apply to this. The CPU my point is, the CPU writes into the VRAM, it always happens right away. It has to deal with crossing the clock domain, which may require some, clock extensions and things like that, pulse stretching, but it can go in right away. But if the CPU wants to read from the VRAM, it can't. It has to wait until there's a hole in time when the main finite state machine is not busy, and that's where this can get deferred. Now we're not going to generate wait states, so I decided to get cute with this. And what you're going to see inside here is at all times, the VRAM will pre-read what would be the next byte that would be delivered if the CPU keeps on reading here. Because it's always knowable. The CPU has to send an address over there before it starts reading. Read. And every time it reads, there's an adder in there that will increment the current address to the next one. And as soon as that's done, which is one pix clock after we send the read data to the CPU, it can immediately advance its address for the next time it's going to read, and it can even do the read in advance and hold it in a special register inside the VRAM. You'll see that in there too. Until and in case, and until the CPU decides to assert the read tick, and then the data is already available. That way we don't have to use wait states and slow the CPU down, because who cares if we pre-read a byte? It doesn't hurt anything. So this thing has a little 1-byte cache in case a read comes along to get the next value. That way it can immediately return it when DMA address is not overriding the thing and read tick goes true for one cycle. It'll immediately send out the value. Okay, after which it'll increment the address again and so on. Okay, so we'll have a look-see at that as well if you want to look ahead and knock yourself out. Then we got the VGA sync generator. This is very much the same as the one I talked about some time ago. Again, if you didn't see it, look at the playlist. There'll be a link in the video description below on YouTube. Very much the same, but I've added a few things. I can configure it to generate different synchronization information. Like I'm in text mode. And remember, in text mode, the VDP has to generate 6-bit wide patterns when they're being rendered on the display. When it's in graphics mode, they're 8 bits wide. So the idea here is that when you generate the clock signals and you're counting out your columns and your rows and all this other fun stuff, it needs to know whether it's dealing with the multiples of 6 or multiples of 8. It also, as you will see, affects where the borders are, because there's 2 pixels that are missing in text mode. There's 1 pixel on the left and 1 on the right. It's narrower than when it's in graphics mode. So what's also been added in here is video active 0, which goes true 1 pix clock earlier than this, because I found that useful. There's a sprite tick thing we'll talk about when we get to sprites. This goes true for 1 cycle at the end of each active scan line when it's done rendering all the patterns, as an indicator to the main finite state machine that this would be a good time to go out and get ready to render all the sprites on the next line. It's sort of like that last pixel thing down here that generates the interrupt request we talked about earlier. This is for the CPU to render a whole frame starting now when that thing goes true. This is going to go true when it's a good time for the VDP itself to go in and prepare for the next row of sprites. Okay? What else we got here? We got a call last and a row last. We got some other indicators in here. I don't know if I use these, but it outputs them to let me know if I'm on the last column of the current row. It's very much like the sprite tick, but not quite, as you'll see when we get there. And this is also useful. I'm on the last row of the screen. In my mind, I thought maybe I'd use this to generate the interrupt signal, but in reality, it was more useful to generate a single tick signal that is true for 1 pixel at the end of the whole frame. So whether I use these or not, I don't know. We'll see how they're generated in VGA Sync, and we'll see if they get used by the time we're done. Who knows? Whether or not they get used in the state machine, I don't know. And there's the border active signal that's also been added to the whole VGA synchronizer to let me know when the border is active. Remember, on the VDP, it's the area around the screen. I don't know if they got a nice picture of it in here. They probably do. Oh, here you go. So what they have is they have the image in here, which I call the active display area. I think that they do that too somewhere. External, default, blah, blah, blah. I don't know. In one of their docs, I think they do that. And this little strip around here is the border. Now, when we map this whole thing onto a VGA screen running in 640 by 480, the border's a little wider than this. They do this on purpose because on NTSC, there's a thing called overscan, and TVs used to cut off and off a lot of the border around here. So you'd have to have a pretty big inset in order to make the thing visible when you're using that kind of technology. For us, we use the border because it doesn't fit exactly in VGA. It doesn't, divide out evenly. So we have about a couple of dozen pixels on the left and then right and the top and the bottom that we, waste on the border so that we still have a border, first of all, because it actually was useful to have colors around the outside. In some applications, they use that to indicate what's going on and to allow us to do even integer division so that all the pixels are the same size on the screen. Otherwise, it would get kind of wonky. All right. So there's a few add-ons in here, but the style is the same. We'll have a look-see at that in a video as well and how these additions work. It's pretty straightforward. You can go in there and figure it out yourself if you really want to. Then we got this big beast down here. All these wires you see going by the way, are the signals that need to exist so that this can output things and have them go somewhere. They output them into these wires, and then these wires get used in subsequent modules. I could put them all at the top of the file. I don't know. I just put them in there as they go because I'm kind of figuring this out as I go, and I need to add more and more as I add more output signals when they're needed. It, of course, needs to know how much VRAM we have because this guy's doing the generating addresses and asserting that DMA mode bit. You'll see that right down here to talk to the VRAM. As usual, reset pix clock. A whole bunch of stuff that comes from the VGA synchronizer is its inputs. It also has these outputs that talk to the VGA, or rather the VRAM, as you know. Down here these are more inputs from the VGA generator. Did I say this right? I don't think I did. No, these are the configuration register values, for crying out loud. All right, these are, yes, there are a bunch of inputs, but these have come from that register interface above. We saw these earlier. These are outputs that it uses to talk to the VRAM and say, do this, do it now. All right, this comes from the VGA synchronizer. You recognize the vertical sync and the horizontal sync. And you'll notice I added in. Okay, down here I have out. And the reason it regenerates these is because the finite state machine has a pipeline in it that's not a short one either. So what's happening is, if you look at this, you see all these signals and times coming from the VGA synchronizer, and then many clocks go by before the state machine forwards those same signals, the H-sync and V-sync, onto the display. Because it needs time to do its work, is the point. And again, we'll see all this stuff when we look at the state machine much more closely down the road. It generates a video active, a border active, and last pixel out. All these are delayed because of the pipeline that's inside here that causes the synchronization signals and stuff like that to be delayed as well. There's your column last and roll. All these are delayed. Okay, these exist as FYI to anything that's using the output of the state machine, as well as the color. So the color value, the pixels here, and the synchronizer outputs go directly to the VGA screen. Okay? And we'll see these in a second right below here. They get used down here. Some of them don't get used at all. And I think I've mentioned this before. Whenever you're generating outputs, right? You know the extra outputs on the VGA sync that we may or may not ever use. It's okay to have them come out of a module. It's okay to even hook them up to wires. If they don't actually ever go anywhere and get used by anything, then what happens is when the circuit is compiled, the optimizer logic says, I got a gate here or a latch or something that doesn't go anywhere. So it just deletes the latch. Who cares? It'll run the same with or without it. It deletes it. Then the inputs on that latch or that gate are left dangling. It then asks, who generated these? Does anyone else need those? If no, delete where those came from. And it runs through the whole circuit and prunes all this stuff off. You'll see that happen in the compiler output. It's like pruning, 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 just getting rid of all this junk. There's two reasons I generate things I don't need. One, I needed them at one point in time because the design called for it. And then later on, I optimized or changed the way something's going to work, and it's still around, it's old and stale. That's one reason. Another reason for these is during simulation, I want to see an indication on the timing diagram when something happens. So sometimes these are just for gratuitously there, so I can see that get my bearings. I can figure out what I'm looking at in the morass of all the output signals, when things are supposed to happen. Is this really the last column? Is this really the last row? Okay, that's another reason that you might find these useful. Someday we can get rid of them if we don't really want them, but like I said, it really won't matter because the tool will remove them. You can check me on that. If you remove color out at the top level and never send it to the VGA screen, almost everything in here will go away. In fact, if you remove H-sync out, V-sync out, not in this file, but in the wrapper, the Z80 vdp99 above, if you never consume these outputs, think about that, right? Why would it ever need to generate a color? Why would it ever need to generate a sync or anything else? An enormous amount of circuitry in here will just get pruned away and thrown away. If you then don't use this and don't use that, then this whole module has no purpose. The entire thing will go away if you just comment those out when this is instantiated in the Z80 vdp99 that we talked about last time. All right, I'm just saying. So don't worry if there's extra junk in here. It's not wasting resources. It will optimize it away. So where does some of this get used? Well, VDP blank is one of the bits in a configuration register with a stupid name because it's blank when it's false. You want the screen to be blank. And if it is not blank, we're going to be rendering a border color or a pixel color in the active region of the screen. Okay, so that's what this thing does here. I could have just as easily used a wire with a continuous assignment with a couple of question mark operators and done a triply nested thing. I felt this was easier to read in this form. Normally, you don't want to have an always block in the same module with a bunch of instantiations. You don't want to mix these. I think I explained that once before. It makes it harder to test. But in this particular case, it's just some simple combo logic. I'm breaking the rule. If it really was important, I could just use some nested question marks. All right. Now, I'll also observe this. It's not necessarily easy. In fact, it may be impossible for the compiler to figure out that these are mutually exclusive and that this is a parallel case, which is why you explicitly have to say that here. Or may be necessary to explicitly have to say that here. It's pretty good at figuring it out when it's, blatantly obvious. But this may be dependent on a lot of things because they come from up in here, right? Video border active out. Yeah, these two things are fairly complicated, and they may depend on, for example, if I'm in text mode or not. These will change at different times because the borders are wider in text mode. So the compiler can't know that it's impossible for these two to be active at different times. Is that true? I don't know. It depends how these are really generated. If they're generated using like a question mark operator inside the state machine, I happen to know they're not, then it could know. All right, but if it can't know, like I said, depending on how it's implemented down there, it won't be able to figure out which of these is true. And the reason I'm on about this right now is because if you use a question mark operator, and I've talked about this before, you will get a priority encoder, which is going to use potentially more LUTs and run more slowly than you would if you got this situation in here where you got a one-hot parallel case, which is really it can be implemented with a MUX with a simplified decoder. Okay, this is a more efficient way to do it. It may not be when you have only two cases, but when you have, as this starts getting bigger, and you will see that in the state machine big time, I can assure you it will use less resources in that case. All right, so this may actually be more efficient than a couple of question mark operators if you do it the other way. All right, I'm just saying. So that's what's going on here. It decides whether it's going to be black, okay, or if it's going to be the border or the actual rendered pixel color and stuff like that. Now down here we assign the actual outputs of the module. This is a style that I tend to use. So the color output, HSync and VSync, come from color reg, HSync out, and VSync route. Color reg is where? Oh yeah, that comes from in here. Color reg is the output of this combinational logic block here. Yes, okay. And the HSync and VSync come directly from here, and they have to be delayed, like I said, due to the pipeline inside the FSM. So there you go. There's your output for your VGA screen. Your output for the interrupt and stuff like that come from here. If the interrupts are enabled, the actual IRQ here will go out of this circuit. This actually will end up at the CPU. Ultimately, this is the real deal from the VDP, the chip, as it were. If it's if they're enabled, then go ahead and forward it out. This here represents the value of the status register. I don't currently have all the sprite stuff done, so it doesn't know about the fifth sprite yet. And as you recall, the bits in the status register, the most significant bit is the IRQ status. The rest of the bits are whether or not there's the fifth sprite on the same line, and if there's a collision between two sprites taking place, as well as what the fifth sprite number is. Okay, so for now I just have zeros in there, but these will come out of the state machine if I continue using the style of implementation I've been working on. That's where that'll come from. This down here is related to this reading from the VRAM, and what's happening here is because the DMA from the finite state machine takes precedence over the CPU's ability to advance that the address in there when you're doing subsequent reading. Okay, it could have to be deferred. So this is probably not a good name for this. I'm looking at it. The reason I named it DMUX is because I wanted to create a signal that was more suitable for use in a DMUX, which is what's going on down here, which is really a MUX. I don't know. Not the best name, but the point is this thing deals with that delay. Okay, so what happens is if I'm not in DMA mode, then this is told now would be a good time to capture the data that's coming out of the VRAM. And that's why the VRAM D out goes in here. The output of this is this DMUX in here. So what happens is the data out from the VDP, this is one of the ports. When CPU read tick is true in mode 0, it wants to read this value here, which is that special cached byte that this thing captures at the right time when the FSM is not in the way, okay? And it sends it back to the CPU. If the CPU is reading in mode 1, it wants to read the status byte from the VDP, which is the value up here. So that's what's going on with this thing. This is kind of wonky, but it exists because of the way that the addressing and the prefetching of the data bytes for reads works. We don't need it for writing, again, because the CPU, or rather the VRAM, has two separate ports. It has a special port for writing, and no one ever writes into it but the CPU, so it has access, immediate access at all times, whenever it wants. So I don't have to do that way, all right? So that's what's going on in this file. At this point, we'll just look at each of these modules, and you'll get the full picture. Eh? What do you think? Let me know in the comments below. Thanks for watching. I'll see you next time.